everyone, welcome back. In this particular video, we will be discussing the problem find local peak. Write a program to find the peaks in a given sequence. Now, what is a peak? You can say peak is nothing but such a given element which is maximum kind of manner. The condition or the criteria when a element is said to be peak is defined now. A element is a peak element if it is greater than its neighbors. Who are the neighbors? The element to the left of it, the element to the right of it. That is, a of I will be considered a peak if a of I is more than a of I minus 1, that is a previous index element, as well as and operator, as well as it should be greater than array of I plus 1. And as you can see, it is strictly greater condition. It is not like if the left neighbor is equal to the current node, then also it is a peak. No, it should be strictly greater than both the neighbors, then only it will be considered a peak. But there are certain corner scenarios which we have to figure out, which is actually given in the question itself. What is given? For the leftmost element, that is the array's 0th index, can you say that there is any left neighbor? No, there is no left neighbor in that scenario. So in that scenario, you only have to check to the right of it. That is, array of 0 will be checked only with array of 1. If it is greater than array of 1, then yes, you can consider array of 0 as a peak element. We will also take some examples to understand this. Similarly, for the rightmost element, that is the array's last index, what we can assume is that we only have to check with the left neighbor of it, because right neighbor will not exist. There will not be any element after the last index n minus 1. So in that case, array of n minus 1 should only be greater than array of n minus 2. Then it will be considered a peak element. So these two are some corner cases which we have to think and then only code particularly. So the example which they have given is arrays containing 10, 5, 6, 3, 4, 8, 9, 15. Let's just quickly write the indices for them: 0, 1, 2, 3, 4, 5, 6, 7. Obviously, indexing starts from 0 in all the languages. And which elements will be considered peak? Let's first think about the corner scenarios. Will the 0th index, the leftmost element, will it be considered a peak? There is no left neighbor, so don't compare it with it. There is a right neighbor which is smaller than 10. 5 is smaller than 10. Yes, 10 will be considered a peak. If you will draw it in the form of a graph, then 10 will be something like this. Then there will be a 5 value. And obviously, if there is nothing in the left, you can assume there is minus infinity in the left. That is, nothing means as minimum as possible. So you can see 10 is a peak. Now going from 5 to 6, you can say that 5 is not a peak because 5 is actually less than both the neighbors. However, it should be greater than both the neighbors. So it is just inverse of peak, which is actually known as valley, which is also a follow-up problem. If you want to calculate or find out all the values, then in that 5 will be counted or 5 will be printed. What about 6? 6 is greater than the left neighbor, that is 5. But what about the right neighbor? Right neighbor is 3. Then yes, 6 is also a peak. 10 was a peak, 6 is a peak. It is strictly greater than both the neighbors. What about 3? Of course, 3 is not less than, it is not greater than the left neighbor, so it is not a peak element. 5 is not a peak element. What about 4? 4 is greater than left neighbor, which is 3, but it is not greater than the right neighbor, which is 8. So 4 is not a peak. It should be greater than, strictly greater than both the neighbors. Right now, it is only greater than 3, not greater than right neighbor, which is 8. What about 8? Similar scenario for 8. It is greater than 4, but not greater than 9. So 8 is also not a peak. What about 9? 9 is greater than 8, but not greater than 15. So 9 is also not a peak. Let's say even if this value was not 15, if this value was 9 itself, then 9 can still not be a peak. Why? Because the right neighbor cannot be equal. But right now it is 15. What about 15? There is nothing in the right side. So again, you can assume minus infinity. There is 9, which is lesser than 15. So yes, 15 is a peak. So how many peaks were there? 10 was there, 6 was there, and 15 was there. You can say there are in total 3 peak elements present, and we have to print all 3 of them. We don't just have to count the peaks, we have to print all of them. And since we need to print all of them, now we are actually discussing the approach. Do we need to go to each and every element and check whether it has a peak or not? The answer is yes. If we are not going to each and every index and checking whether it is peak, how will you be able to print all the peaks? If question was maybe print only one peak out of them, then you can think of some optimization, then you can think of some divide and conquer or binary search, whatever you know. But right now, since it is just a simple linear traversal approach, we are going to do a linear search kind of strategy. That is, we will be linearly iterating over the array, checking whether each index follows the criteria, follows the condition, whether it is a peak element or not. So just go to each and every index and check whether array of I is greater than array of I minus 1, as well as and operator, or whatever the operator is in your programming language. Usually it is represented by ampersand symbol, as well as array of I should be greater than array of I plus 1. But before applying this condition, if a element is greater than both the neighbors, strictly greater, you also have to ensure whether array of I minus 1 exists or not, whether array of I plus 1 exists or not. If not, then take the value as minus infinity. That is, instead of just directly comparing with array of I minus 1, take a variable, let's say left neighbor. Take a variable, let's say right neighbor, and do what? Initialize the left with minus infinity, or you can say the minimum value which your data type can store. Let's say for integer, it will be the integral's minimum value. And then you can compare whether array of I is greater than left neighbor as well as right neighbor. If left neighbor and right neighbor does not exist, let it be minus infinity, so that this condition always gets true. And if it is existing, then update the value with array of I minus 1 or array of I plus 1 respectively. So now, since the approach is clear that we don't have to do anything apart from linear search, we have to go to each and every index, check the condition. If it is true, then obviously print the element, because we have to print the values, not the indices. That is also important. A linear traversal, that is linear time complexity, or you can say order of n time complexity, where n is representing the number of elements in the array. And what about the space complexity? See, when we are traversing over the array is given to us as an input. Whenever we calculate space complexity, we never include the input spaces in it. So since input is a array which is not going to be considered as extra space, auxiliary data structure, space will be constant. Why? Because there is no extra data structure which we are creating in order to do linear search. Linear search is just in place solution. So space is a constant, you can say order of 1 space complexity for this particular approach, and the time will be linear. And the answer whether we can optimize it further is no. Why? Because we have to print all of the peaks, and that is not possible to do without doing linear search, or you can say with using binary search, or maybe with divide and conquer. So now, since there is only one approach, there is nothing much to discuss in the second milestone, which is the approach part. Let's just now directly jump on to writing the instruction manual, the pseudocode. So what we have to do is, we have to, let's say, create a list, because we have to not print the elements, but we have to return them in by storing them in a list of peaks. So create a list of peaks of integers. Of course, the list will be empty. Initially, it will be empty. And of course, you have to make it as a dynamic array, or you can say a vector in C++, array list in Java, and so on. So a dynamic array should be created. Run a loop over all the indices of the array. That is, run a for loop from 0 till n minus 1. Let's say the for loop is working for index from 0 to n minus 1. Find out who is the left neighbor. And if you are saying that left neighbor should be array of I minus 1, then that will be incorrect. Why? Because it might happen I minus 1 index does not exist. So store left neighbor value as array of I minus 1, or you can say index minus 1, that is the value at previous index, if it exists. If index minus 1 exists, that is, if it is within the range of 0 to n minus 1. Otherwise, take it as minus infinity. Otherwise, take it as minus infinity. I'm just writing minus inf to represent minus infinity. It depends in your programming language, how will you define the minimum value of an integer or minimum value of your range. Similarly, you have to store the right neighbor value in a variable right as array of index plus 1. But same thing, that if index plus 1 exists, then only. Otherwise, if index plus 1 does not exist, then you have to do what? Take it as minus infinity. That is a minimum value. Then only this criteria will be fulfilled, that you are only comparing with left neighbor, you are not comparing with right, because even if you compare with right, it is minus infinity, so it will always be true. Any value will always be greater than minus infinity. Same for left one. Now, since we have taken both the variables, what we can do is check if the current element is peak. If array at index is more than the left neighbor, as well as the array of index is more than the right neighbor, both the neighbors are smaller, so the current element is peak. And as you can see, we are checking for strictly greater than value. Then we can add the current element, you can say that is array of index in the list of peaks, And finally, once this entire loop is done, what we can do is we can also return the list of peaks. That is all what we have to do. Linear time complexity, constant space. Why? Because we never include the input space, output space. Input is an array, output is a list. Apart from these two data structures, there is nothing extra auxiliary. That's why constant space is there. We will be now discussing the milestone 4, where I will write the code particularly in Java programming language. You have to also watch, or you can say we have to also discuss about the time and space complexity again based on the code which we will be writing. So we already have the instruction manual written for us. What we have to do is in Java, how to create a dynamic list, that is by using list on the left hand side. However, if you want to make it as an array list on the left hand side, you can do it. But since we need to return a list, it is better to have a list on the left hand side. That is, we are creating a list, but how we are creating it? There are different ways of creating it. There is a array list way, linked list way, then there is a other way known as tag also. But right now, the easiest way is nothing but array list. That is a dynamic array which can grow in size. Initially, it will be empty. Initially, it will have 0 elements present in it. And now what we have to do is we have to run a loop over all the elements of the array, that is starting from the 0th index, going till the last index, which is n minus 1, or you can say less than n, checking whether the current element is a peak or not. But before checking, we have to find out both the neighbors of that element. So we will say, who is the left neighbor? Left neighbor is array of index minus 1. But array of index minus 1 will not exist if index minus 1 is less than 0, because left neighbor will not exist. If index is 0, index minus 1 will be minus 1. So if index is a 0, then in that scenario, what do we have to do is we have to take the left neighbor as integer dot min value. That is minus infinity in Java. Otherwise, we can take the previous index value, because before getting the value of a given index, you have to ensure whether the index exists or not. Otherwise, it will give you a index out of bound exception in Java. So if the previous index does not exist, take it as minimum value. If it exists, take it. So I'm using a ternary operator. This is nothing but equivalent to a if else condition. Just the way of writing if else is replaced by a single line statement, which is ternary operator. That is, this is the condition. If the condition is true, evaluate the expression after question mark. And if it is not true, that is false, then evaluate the expression after the colon. What to do for the right value? Right value will exist at array of index plus 1 instead of index minus 1. But again, when this index will be out of index, out of bound, we will say when the current element is the last element, that is, the current element is the last index of the array, then the next element, the right neighbor, will not exist. So again, we have to take the integer dot min value in that scenario. And if it exists, we can take the value as done in the previous line also. Now that we have both the neighbors, the left neighbor, the right neighbor, now is the point we can surely compare whether the current element is strictly greater than the left value as well as the right value. If it is, then we can say the current element is a peak. So in that scenario, what we can do is we can just add the current element in the array of peaks. Let's rename this array of peaks as peaks, and we will say peaks dot add the value which is array of index, because we have to print the values, not the indices. And finally, we can easily return the peaks. That is the dynamic array, or you can say the array list. Let's quickly run this. It is not a hard problem. Actually, it is a very easy problem. If you know linear search, most probably you should be able to do this on your own also, even without watching this current video, which right now you are watching actually. The reason is this kind of corner scenarios are a little bit, you can say, trickier to find out. That's why we have included this problem for your practice. But since you can see the sample test case is working, let's just submit also to confirm whether all the corner scenarios will work or not, where the leftmost element is the peak, the rightmost element is the peak. And there will also be one scenario where you have to think yourself what will happen if there is only one element in the array. My code will even work if there is only one element in the array. Let's say the element is 10. So if there is only one element in the array, there will be no left neighbor, no right neighbor. Of course, we can assume minus infinity, minus infinity. So of course, 10 will be a peak. So in that scenario also, this code is correct. You can say index will be 0, n minus 1 will also be 0. That is, in both the scenarios, take minus infinity only. So don't just cram the code or don't just cram the approach. Try to think of the various boundary scenarios and also try to think of the time and space complexity, which you can easily see is linear in terms of time, because we are just running a loop over n elements of the array, order of n time complexity. What about space? There is an input array, there is an output list. Apart from the input and output data structures, there is nothing else which we are creating. And when we say space complexity, we only consider the extra space, the auxiliary data structures which we create. And we have not created anything apart from input output to solve this problem. That's why the space complexity is constant, order of 1. So that was the last milestone for the problem. With that, we are done with it. We will meet in a new video with a new problem.